Good morning. We have 2 or 3 more minutes, and then we can get started. Well, does anyone of you have any questions regarding the course? We'll share my screen and see what happens. Almost there. I always find that this is a nuisance. It always blocks my PPT. Does anybody have any idea as to where I should put this thing? A good place to put it can be at the bottom. I hope the stylus is working well today. Why don't you guys turn on your video camera so that I can see your faces as well. And it adds a human touch to this online teaching. And as you know, Zoom will become more and more commonplace. I was Zooming with NSF yesterday without traveling there. And all the members of the panel were on Zoom and we could see their faces. At least it doesn't make it look so inhuman if you don't have your faces shown. Jian, you want to show your face? Jian Wang? I guess he or she doesn't want to show the face. Okay, let's get started then, okay? Let me put this at a place that doesn't block the screen. Maybe it might be better to show it this way. Okay, today I'm going to talk more on constitutive relationship and uniform plane wave. So I will begin with more on constitutive relations, then talk about isotropic frequency dispersive media, anisotropic media, bi-anisotropic media, inhomogeneous media, uni-axial and biaxial media, nonlinear media. I'm going to go through 7.11 to 7.16 quite quickly. And then I will talk about 7.2 and 7.3 in more details. Okay, let's get started. Any questions before we get started? Can you see my screen? Good, I see some nodding heads. I presume you can see them. As we said before, we have 4 Maxwell's equations and we only need to solve 2 of them because the third and the fourth are derivable from the first 2. Like we have, I'm going to make my pen a bit thicker today so that maybe I can write better. Okay, and we only use Faraday's law and Ampere's law. And to make things simple, we set the current to be 0, so there's no source in the problem, or the source is at infinity. It makes Maxwell's equations simple. As we said before, if you only solve 2 of these 4 equations, we have E, H, B, D as unknowns, and that is not enough. So we have to add more equations. And the equations are coming from our constitutive relationship. Like in vacuum, we know it to be this one, that the magnetic flux density or magnetic flux is B, which is mu naught H, and then the electric flux density or electric flux is epsilon naught E. And then we will have 4 equations and 4 unknowns to solve this problem. Usually we use epsilon naught and mu naught to denote vacuum, permittivity, and permeability. Okay, mu is called the permeability and epsilon is called the permittivity. It's very important to know that the term that we have, D, give rise to something called the displacement current. And displacement current is very important in electromagnetics or electrodynamics. And usually D is written as we have learned before, the vacuum contribution plus P, which comes from material. Okay, and P can be coming in different ways, and we will start with linear medium. For linear medium, P would be assumed to be linearly proportional to E, the electric field. So it's usually written in terms of epsilon naught chi naught E. Okay, and sometimes just written in terms of chi E, and this assumes linearity. So what is P? P is the consequence of small electric dipoles formed in the medium when you have a electric field in a medium. I can write this as epsilon naught chi naught E. This electric field will polarize the medium, and then the medium becomes filled with small little dipoles. And those small little dipoles will look like this in the medium. And you can think of them as acting like a series of capacitance. You can see that this is an insulator, but you can think of capacitor here, and then a capacitor here, and then a capacitor here, and so on. And then maybe another piece of wire. So you can think of when these little dipoles are formed, small capacitance or small capacitors are filling all of space. And as we know, if we have a time varying current, if d dt is not equal to 0, then electric current I, a phasor I, can flow through a series capacitance. By the same token, if we have many of these dipoles lined up in space, they can give rise to displacement current flow, which is very much like electric current flowing through a series of capacitance. But we can also think of this relationship as a linear relationship where this is input and this is output. And if you think of this as a linear system, then it's very akin to the linear time invariant system that you have studied in electrical engineering. This is usually called LTI, the LTI system. And if you have an LTI system, this is not the most general relationship between input and output. The most general relationship is actually that given any point in space, you have this polarization density, and it should be linearly related to the input through a convolution. And that convolution chi can also be a function of space, but it will be convolving with the input. And hence, this forms the most general relationship. Or maybe more, okay, because you can even get more general relationship than this of an LTI, okay? Because of this, then this is called a convolution. That's why the term convoluted also applies. And you know how to write it down as an electrical engineer. So I won't write it down for you as to how you convolve the input with the system's response. This is like the system's response or the transfer function. Some people will call it a transfer function. And then the output would be P. And the wonderful thing is that for linear time invariant system, if you go to the frequency domain, this relationship becomes very simple. This now is a phasor. And then the transfer function is just becoming a phasor again, a complex number. And then this is what happens in the frequency domain. And all these P, E are phasors. And chi is what we call the transfer function in electrical engineering. Okay, any questions regarding this? So this is wonderful. This allows us to do things very simply in the frequency domain. And I'm going to talk about dispersive medium. Dispersive medium is the case when chi is a function of frequency. When this happens, then the medium is dispersive. And because of this, you can define a relationship, for instance, that when you have D, R omega, which is epsilon naught E plus P, and that relationship becomes epsilon naught 1 plus chi. This should be a plus sign, P. Then this is now in the frequency domain. Sorry, this should be E. Okay, and hence you can define a effective permittivity, which could be a function of position times E. This is usually called the effective permittivity. Okay, and this is what is a frequency dispersive medium. So So epsilon is in general a function of frequency. When epsilon is a function of space, function of R, then we call the medium to be inhomogeneous, or another English word is heterogeneous. Okay, so heterogeneous medium is quite complicated, but you need usually a computer to solve this kind of problem. In this course, most of the time, we will assume that epsilon is independent of R to make things simpler, or we make epsilon to be a piecewise constant function of R to make things simpler. But with this definition, you can extend this concept to an isotopic medium. Okay, an isotopic medium is the case where the relationship between the input and the output is not through a scalar number. Like in general, we have D is epsilon naught E plus P, the material contribution. And if the material contribution is not a simple relationship anymore, but to a relationship that is more complicated than the scalar number, you can have a matrix relationship like this. This is, you can think of this as a 3×1 vector. If you want to think matrix algebra, this will be a 3×3 matrix. Okay, and then you can think of the output here as 3×1 vector. Okay, chi is analogous to a matrix in matrix theory, but when chi is used to relate to physical quantity, we give it a special name. Chi is the tensor. It has a physical notion that it always relates to vector quantities. And when that happens, we call it the tensor. Okay, so a tensor is usually represented by, for instance, a matrix, because it essentially is a 3×3 matrix in disguise. For instance, one example of a tensor is something that looks like this. Okay, and if you have such a tensor, you will see that when you lump everything together, you lump these two terms together, you can write this part as D has been an effective permittivity tensor, dotting with E. Okay, you can see that when this happens, D and E do not point in the same direction. Can you see that? Can everybody see that? That is, when you have epsilon as a permittivity tensor, and E, if it is pointing in a certain direction, D need not have to point in the same direction as E. Can everybody see that? Or you have to visualize this in your head. I see some nodding heads, so good. So this is the effect of an isotopic medium. You can work this out quite easily. When epsilon 1 is not equal to epsilon 2, is not equal to epsilon 3, this is a terminology used quite often in optics, because in optics, you do come across this kind of an isotopic medium quite frequently, and this is known as a biaxial medium. However, if you have epsilon 1 equals epsilon 2 not equal to epsilon 3, then this is called a uni-axial medium. And if you want to visualize this in your head, what happens is that if you think of this as relating the xy component, like this is ex, ey, ez, and so on, okay? And if you plug in E in there, you will find that for the case of uni-axial medium, if you keep yourself in the XY plane. The vectors are pointing in the same direction in the XY plane. Only the third axis, the Z axis, the electric field in the Z direction will be modified in the case of the uni-axial medium. Can you see this? If you put yourself in the XY plane, then the medium that you see would be something like epsilon 1, 0, 0, 0, epsilon 1, 0, 0, 0, epsilon 2. Okay, and if you multiply this by EX, EY, EZ, your D, in the two-dimensional space involving only EX and EY, the two permittivity are the same in the X and Y direction. Okay. Any questions regarding this? Well, let's see if we can go to looking at bi-anisotropic medium. Bi-anisotropic medium is the generalization of the isotropic medium. And in this case, what you have is that you could have the D being dependent on both E and H. Okay, and in the textbook, it's usually written, and this is called a kasi in Greek notation. And then the B will be written as mu dot H plus zeta dot E. Other than the name, you don't have to learn very much about this media in this course. The fact that they do exist materials in this world where the electric flux density is dependent on both E and H, where the magnetic flux density is dependent on both H and E. You just have to know that this media exists. Other than that, you don't have to worry about that too much. Okay, and of course, I just talked about inhomogeneous medium. So inhomogeneous medium, where if these are functions of space, and then this zeta, this is kasi, this is zeta. That's how you read them. And they will be functions of space. And I just talked about uni-axial media, so I will not talk about them now. But I like to talk about nonlinear media. Let me see. Nonlinear media is the case where you have the polarization density. Say the simplest case of a linear medium is this, but if this chi now is something that depends on E, then the medium is nonlinear. And you can go through the test of linearity. Linearity means that you have, this is input, this is your output. You can think of a linear system theory. So I have input E1, then the output is epsilon naught chi E1 is my output. And then if I go through the test of linearity again, if I put in E2 as my input, then my P2 is given by this. And then if chi is not dependent on E, you can easily show that when I have alpha E1 plus beta E2 as my input, the output should be alpha P1 plus beta P2. You can go through the algebra yourself to convince you of this fact. But if you have such a medium where the chi is not a constant anymore, but a chi that depends on the input, the system would be nonlinear. And the test of linearity fails. Okay, this is usually what we call the test of linearity, or the principle of linear superposition holds, but it will not hold for this kind of medium. And you encounter this quite often in optics. This is called Kerr effect in optics. Okay, but you also encounter nonlinear media quite a bit in low frequency electromagnetics. Especially in designing electrical machinery. In designing machinery, you will have to worry about the relationship between the magnetic flux and the magnetic field quite a bit. And in a general medium, this can be generalized to a mu times an h. But then if this relationship becomes where mu itself is a function of h dot h, then the medium becomes nonlinear. And if you have taken an electrical machinery course, you often see this plot where the input is h and then output is b, but you wouldn't get a linear relationship between input and output. You might be linear in the beginning when the h is weak, but as you make h stronger and stronger, the magnet run into a saturation behavior. No matter how strong and magnetic field you put in the system, the magnetic flux will not increase. And then if you reverse the sign of the magnetic field, okay, it will go backward in the other direction, but it has some memory. It doesn't go back to zero again. Okay, so this is called a magnetic permanence. And then the same thing happens in the other direction. And if you put the magnetic field in the other direction, it will go up and become saturated after a certain while. And then if you reverse the sign of the magnetic field, it doesn't go back to its original value. And if you increase the magnetic field in the positive direction again, the B flux goes in this manner. And the same thing happens for the other direction too. And this is called the hysteresis loop. I hope I spell it correctly, hysteresis loop. Okay. And hysteresis loop, as you might learn in advanced courses, the size of the hysteresis loop is proportional to the loss in the magnetic system. Okay. This area here is proportional to the loss in the system. Any questions so far regarding nonlinear media? Okay, if not, then I'd like to talk about wave phenomena in the frequency domain. We have talked about wave phenomena in vacuum. That was very easy to do because then what we did there was to assume that we have E, we have D equal to epsilon E. Okay, it doesn't go away. Let me see. Okay, it wouldn't go away too. Let me do this. So in the previous study, we have studied a vacuum where D is epsilon naught E. Okay, and we also have assumed that mu is mu naught H, B is mu naught H. So that was an easy case to study. But now if we have material media, D would be more like epsilon naught 1 plus chi E. And maybe build the same thing will happen. It might be mu naught into 1 plus chi m. Usually you don't go by such a name, but let me make things simpler for you that there is a magnetic susceptibility, and this usually is called the electric susceptibility. Let me see if I can spell this properly, susceptibility. And if you assume the frequency to be a constant, then this relationship is a simple one. You don't need to think about convolution. So in the frequency domain, this is very simple. And it's a constant relationship And you also can define an effective permittivity, which is a constant if you were to keep frequency a constant. So solving Maxwell's equations in the frequency domain, assuming omega is a constant, or if you have a time down harmonic solution, becomes rather simple. So we can actually solve Maxwell's equations assuming time harmonicity, and that this chi is a constant. So you go back to looking at Maxwell's equations. The only thing that you need to change in Maxwell's equations away from the vacuum case was this. So what you do then is that you just change this to the frequency domain case, where mu can be a function of omega. Okay, and then you have Ampere's law, where in the vacuum case it was, let me see, there should be a minus sign here. I'm sorry, there should be a minus sign. You have learned how to convert to frequency domain from Dr. Na. So whenever you have partial t, you replace partial t becomes j omega in the frequency domain. So in the frequency domain, Maxwell's equation just becomes this. And then you can also say that for the most general case, we have j omega epsilon of omega times E. Okay, there should be a minus sign here. So these two equations are relatively simple to solve. Shall we solve them? Okay, we can solve them by, for example, taking the curl of the first equation. If you take the curl of the first set of equation, then if I assume that I have material medium, and I assume that the medium is homogeneous, so that mu and epsilon are independent of space, then if you take the curl of the second equation, the first equation of the second part, you get curl of E is minus j omega mu. Mu is independent of space, so I would just get curl of H. Okay. And this is a double curl operator, as usually quite sloppily written in this manner, but all of us understand what it means. It means that there should be a parenthesis here, an implied parenthesis that nobody bothers to write. Okay. And then this equation that looks like this, and if I replace this with Maxwell's equation, I take the second equation and replace that, I will get omega squared mu epsilon E is what I get. And then I will get curl of E minus omega squared mu epsilon E is equal to 0. Very much like the wave equation, except that now I don't have time derivatives. All the time derivatives have disappeared in the frequency domain or in the phasor wall. And this is usually called the vector Helmholtz equation. Okay, it's called the vector Helmholtz equation. And of course, we need to simplify this equation to make it simpler. And when you have a double curl operator, if you have gone through this course long enough, you know what to do. What is the curl of E equal to? Anybody in the class want to volunteer to give an answer to add some life to the classroom? What is curl of E? Anybody wants to volunteer? If you don't volunteer, I'll call upon your name. Anybody? Okay. What about Jonathan Warnke? Do I pronounce your last name correctly?
Yep, that's correct.
Yeah, how would that?
So curl of V would be something orthogonal to E, and so another curl would be either E or something orthogonal to the original E, wouldn't it?
Yeah, you got the right point. It's like A cross B cross C. Okay, A cross B cross C.
Are we just going to do or is it the double identity we have where it's B A dot C minus? Is that the identity we use?
The back of the cat formula.
Yeah.
Okay, if you go through your exercise and applying the back of the cat formula with the implication that the parenthesis is there. Okay, I won't go through the detail, but you can do this at home. That this will become gradient of the divergence of E minus del dot del of E. Okay. What did we do with this term? We went through this exercise before in free space in the time domain, and we dropped that term for some reason. Does anybody know what we can do to drop that term? What kind of argument we can have to drop that term? What must the divergence of E be equal to? What about David Alexander? Would you like to volunteer an answer? What happens to the divergence of E?
Was this where was it the Coulomb gauge or something, or was that a different one?
Oh, this is a different one. We are not talking about A, but divergence
that's
of
right.
E, what should it be?
Can you set it to 0?
Oh yeah, very good. You can set it to 0. Because we solved the first two Maxwell's equations, there was also a third and a fourth, which is divergence of epsilon of E. And if there's no source in the medium, or if rho is equal to 0, then this is 0. And if epsilon is a constant for the case of homogeneous medium, then this is the same as this. So using the third equation of Maxwell, divergence of E equals 0. But you can also see it from this equation. As I said before, the third and the fourth Maxwell's equations follow from the first two. And what happens if you were to take the divergence of this equation? What happens to the divergence of the left-hand side, Ampere's law in the frequency domain? Anybody, the divergence of the left-hand side should be?
It goes to 0.
Very good, very good. Okay, who was that who answered?
That was David again.
Oh, David again, okay. So the very good divergence of the left-hand side is equal to 0. And then the divergence of the right-hand side, these are all constants. So the divergence operator would just act on this. And it should give you this thing being 0 again. Okay, so for consistency with Ampere's law, divergence of E has to be 0. So the vector Helmholtz equation becomes quite a bit simpler under this observation. So under that observation, the vector Helmholtz equation just becomes Laplacian of E plus omega squared mu epsilon E is equal to 0. Can everybody see that? Okay, remember that now there's a plus sign there. And this is Helmholtz equation in the frequency domain, or Helmholtz wave equation. And yesterday I just reviewed a proposal where the PI put a minus sign there. No, that's not a minus sign. It should be a plus sign. Okay, remember that that should be a plus sign. And you have come across the wave equation that we have derived before. In the time domain, this would be corresponding to this equation. Okay, this is the scale, the wave equation. Some people call it the Helmholtz wave equation. Some people also call it the D'Alembert wave equation, but it originated quite a bit back in history because these kind of equations were studied by acousticians. Acoustic waves also obey this kind of equations. So it has come into our world long ago. Okay, now that we can reduce the vector Helmholtz equation into 3 scalar Helmholtz equation. Okay, this is actually 3 scalar Helmholtz equation of this form. If I take the XYZ components, each of the components will satisfy this equation. And this is called a scalar Helmholtz wave equation. And how do I solve this problem? Well, let me do a very simple case. Very simple case where I assume that electric field in general in the frequency domain has only an X component. Okay. And this clearly satisfies the requirement that divergence of E equals 0. Can you see that divergence of E, sorry, the right-hand side should be just a function of Z. Okay. If I assume that the electric field is the function of position in omega in such a way that it only has the X component, can you see the divergence of E equals 0? Can everybody see that, or you want me to belabor this point? Okay. What divergence of E is divergence dot of XEX would be partial XEX. But EX is only a function of Z. So this becomes 0. So the divergence E equal to 0 condition is satisfied. Then I will just plug this into this equation. But then with this expression this way, you can also see that partial Y is equal to 0. Only partial Z is not equal to 0 in this equation. So you go back and write down the Laplacian in full, all the other terms disappear, and you only have the second derivative. I'm going to drop the omega terms. The scalar Helmholtz wave equation becomes this equation over here. Does everybody get it? So this becomes, instead of a PDE, this was what we call a PDE, a partial differential equation. This becomes an ordinary differential equation since it has only one derivative. And good electrical engineers, all of you are good electrical engineers, that this is a second order constant coefficient partial ordinary differential equation. And we have solved this problem over and again in electrical engineering. You can write the solutions as linear superposition of exponentials. So if I were to write this in full, I'm going to drop the omega term. I mean the omega dependence, which is implied for all phases. We are working with phases now. The general solution to this problem would be something of this form. Can everybody see that these are the two solutions that you can have to this ODE? It's a second order ODE, so it should have two independent solutions. The two independent solutions can be sines and cosines. It can be also exponential functions. I prefer to use exponential functions. And that you have to be mindful that when you want to convert this back to the time domain, okay, this is a phasor. I usually denote phasors by under tilde, but I don't want to use under tilde all the time. So when you want to convert this back to the time domain, what you do then is to multiply this phasor, Z omega, which is this one over here, by e to the j omega t, and taking the real part. And that will let you go back and forth between the time domain and the frequency domain. Okay, any questions so far? So if you do that, then you can go through some algebra and show that if E0 plus or minus are functions of, I guess, frequency, but also functions of space in a very simple fashion, as I would have denoted in the lecture notes, that it is a complex number. And if it's a complex number, it can be written in terms of magnitude and a phase. Okay, let me denote these two complex numbers in this manner. And you go to the algebra of finding this quantity in the time domain, then you will find that I won't go through the detail. And if you find this in the time domain, you will find that it's 0 plus magnitude cosine of omega t minus k naught z, not k naught, I just use k, okay, times z plus alpha plus, and then plus e naught minus cosine of omega t minus or plus kz plus alpha minus, okay, plus alpha minus. And this is a simple exercise. You just go back and use this formula 2 times and you get these 2 terms. But what does these 2 terms, what do they show you? It is of the form of a traveling wave, because you can write, for instance, the cosine of omega t minus kz plus alpha plus in terms of something that is more like a traveling wave function. So you can write this as omega over c times c naught, not necessarily c naught ct plus z. Let me see. Should be a minus here, and then plus alpha plus. And this is of the form of fct minus z. And you have learned previously that when you have a function like this, it corresponds to a traveling wave. And the velocity of the traveling wave is c. Okay, this is, and then the other term will be a traveling wave with the velocity of minus c. So this wave travels in this direction, this wave travels in that direction, and this corresponds to a wave traveling in that direction. Okay, so I like to use the last 5 minutes to describe uniform plane wave. Okay, let me use a new slide. In the case of a uniform plane wave, we solve the vector Helmholtz equation in its full glory. We will not make simplification, no mincemeat, okay? So we solve the vector Helmholtz equation in its full glory. It will look something like this. And then, as we said before, this equation can be converted into something that looks more like this, using the back of the cat formula. And then you can now assume that the electric field, which is a function of position, and so on, but it can represent a plane wave propagating in all different directions. Okay, can you hear me? Hello, can you hear me?
Yes.
Okay, good. So this would be, I can assume that this wave is a wave that is propagating like this, and then as a shorthand notation or compact notation, I can write this as minus k dot r. This is a compact notation to write out this long thing, because k will be given by xkx, a vector, yky, plus another vector zkz. And then r, of course, is the position vector that you might have learned in some undergraduate courses. And if you dot the two together, You take the dot product together, you get what you have in the exponent. Okay. What happens is that if you plug this expression back into the scalar Helmholtz wave equation, the Laplacian, which is del dot del, becomes just partial square partial x squared plus partial square partial y squared plus partial square partial z squared. Okay, you can go through the algebra yourself, but there's a simple rule of thumb here that if you have a function that has a dependence like that, the del operator just becomes minus jk, which is minus j x k ky plus z kz. Okay, so if you go through the algebra, you can show this to be true. And in general, when you plug this in there, you will have Laplacian, which is del dot del becomes minus k squared, where k squared is equal to minus kx squared plus ky squared plus kz squared. Okay, you have this to be true. And then if you plug this expression, this equation back there, you will get the fact that minus k squared, which is the expression that we have above there, plus omega squared mu epsilon times E is equal to 0. And hence you get the requirement that k squared must be equal to omega squared mu epsilon. This is called the dispersion relationship. Let me see. If you write this out in full, it says that kx squared plus ky squared plus kz squared must be omega squared mu epsilon. This just says that if you have a vector k that is pointing in different directions, because this vector k can have different components, kx, ky, and kz, it can point in arbitrary direction, but this is a vector with a constant magnitude. This is just a measure of the magnitude of k. If you take the magnitude of k, you will find that it will be kx squared plus ky squared plus kz squared square root of. So this is magnitude square of k. And this is just an equation of a sphere. Okay, this is, if you think of this as an equation in a 3D k space, this is the equation of a sphere. And that sphere is called the Ewart sphere. So if you keep the right-hand side a constant, which is the case when you operate the system at a constant frequency, then this is true. And this is called the dispersion relationship for a plane wave. Okay, so you can further show that, let me see if I have this picture down. Strange that I have this picture over here. That if you have a plane wave that you can write, let me see if you can pull it down. Okay, so if you can have the solution, if the solution can be written in this manner, that is, if you can write the solution in this manner, the solution is of the form of e to the minus j k dot r. And this actually denotes a plane wave propagating in the k direction. And all these constants over here, all these planes over here, the face front of the plane wave will be a constant. So this is a plane wave front. And you can go back and convince yourself that this expression is the expression for the plane wave. And you can further show that, well, the electric field, the magnetic field, and the k vector have to be orthogonal to each other, and they will have a system that looks like this. I will write this out in greater detail in the lecture notes so that you can read about this, and I will not talk about it so much in this lecture. I have to stop here because it's already 11:22. Are there any questions that you would like to ask before we leave each other? Any questions, anybody? If not, I'll let you go then. And there is an office hour tonight that you can go and attend. If you have any question, you can bring questions you have about the lecture notes and so on. And we can answer your questions in the office hours. Okay. See you later then.
Thanks,
Thank you for
Professor.
coming. Thank you for coming.
Thank you.
Bye-bye.